Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Okay, so you see what we have so far. We have a matrix that mathematically describes the effect of a quadrupole magnet on a proton as it circulates around the booster synchrotron at Fermilab, okay? Using those different mathematical tools from our toolbox, right? The last one being linear algebra, we're able to use a matrix to describe the effects of a quadrupole's magnetic field on a proton that has a positive charge as it passes through that quadrupole magnet. Now, it's very similar to optics, right? Lenses. Optical lenses are used to keep a beam of light collimated over a long distance. And let me show you a diagram of that. Okay, here you can see how a beam of light is collimated, right? Is focused by an optical lens, all right? Here's the beam of light. Here's the optical lens, and it focuses it, right? And then another type of optical lens collimates it. So these quadrupole magnets, they are performing the same function, but instead of focusing a beam of light, which is what these optical lenses are doing, they're focusing a beam of protons, okay? And what's kind of interesting is that a beam of light travels at the speed of light, right? 186,000 miles per second, okay? Now, these protons, they're not traveling at the speed of light. They're traveling close to it, and cosmic rays that reach us from outer space, very, very close to the speed of light, okay? And actually, that brings me to a point, and I'm going to stop sharing screen right here. But here's the analogy between a beam of light traveling at the speed of light being focused by optical lenses and collimated. And then you have our quadrupole magnets that are focusing a beam of highly energetic protons that are traveling close to the speed of light, but not near to the speed of light. Okay. Okay. So you see the analogy here, right? A lot of analogy between optics, the area of physics that studies light, and high energy physics, which studies highly energetic particles like cosmic rays. And as I said, there's implications in astrophysics. So I thought I'd just put this little tidbit in because you might be wondering, why is he continuing talking about what was going on at Fermilab and with the protons in the synchrotron? And he keeps referring to cosmic rays. Well, with all of our technology, particle accelerators like Fermilab, the Fermi National Accelerator Laboratory, and the Large Hadron Collider, LHD, LHC, right, in Europe, right, that try to attain the energies that cosmic rays reach us with from somewhere out there in outer space. So my thoughts are that the research that I did in high energy physics at Fermilab, you're looking at highly energetic protons circulating around a synchrotron. Well, what is it in nature that is able to do the same thing with much, much, much more powerful protons? I mean, cosmic rays, they're at a whole nother level than the energy that's able to be attained in the particle accelerators here on Earth, right, with the protons. So, just as in a synchrotron at Fermilab, you need quadrupole magnets to collimate those protons. What in nature is serving as a quadrupole magnet, right? And naturally, not human-made, obviously, and able to deal with protons that are magnitudes more powerful than what is able to be produced in the particle accelerators here on Earth, okay? So again, because there's a connection between the two, the earthly attempt to accelerate protons at very high energies, and the natural reality that protons somewhere out there are accelerated at huge, huge speeds. Supernovas being a top candidate. So again, I find it very interesting to go through this research, which was to be able to keep track of the protons as they circulate around the synchrotron. I find it very interesting to think about what in nature keeps track. What is the mechanism that keeps cosmic rays collimated as they reach Earth? Or are they just a cloud of protons that hit Earth? But no, I think they are collimated to a degree. So what mechanism is it out there? It's not quadrupole magnets, right? So again, we'll continue on. I'm just talking about small segments for us all to digest this, because when it hit me of how much this research that I did could have applications with astrophysics, why not, right? Okay, so let's go back to that paper. Okie dokie. Okay, so here's our matrix. It's a 4x4 matrix, all right? And there's a reason for that. You remember the equations of motion that are needed to specify the position of any object. You need its position, and you need how fast that position is changing with respect to time or with respect to another variable. And we used a lot of mathematics to get that change with respect to the z-axis, the trajectory of the protons as they circulate around the synchrotron. So over here in this column, x is the horizontal position in phase space with respect to the z-axis. Let's jump down to y. Y is the vertical displacement of that proton with respect to the z-axis, okay? The trajectory. X prime, that's how fast or how much that horizontal position of the proton with respect to the z-axis is changing with respect to how far that proton has went down the z-axis, okay? And y prime, that's how much the vertical position of that proton has changed with respect to going down the z-axis, okay? Not with respect to time, neither one, but with respect to that proton's distance through the page, down the z-axis, okay? So, you have 4 elements, x, x prime, y, and y prime. Okay, now, here comes our 4x4 matrix. Because we have 4 elements, we need a matrix that's 4x4. If we had 2 elements, let's say we just had x and x prime, then we would only need a 2x2 matrix, okay? But we have 4 elements, so we need a 4x4 matrix to express the effect of a quadrupole magnet on the motion of the proton in phase space, okay? Now, in this instance, we're talking about a quadrupole that is radially or horizontally focusing and axially or vertically defocusing, okay? That's what this magnet is. Remember, 24 cells around the booster synchrotron at Fermilab. Each of those 24 cells contains 2 quadrupole magnets. One like this, and then the other one, that's the reverse, okay? Axially or vertically focusing and horizontally or radially defocusing. And to represent that type of a quadrupole, you see these 4 elements right here, and you see these 4 down here. To represent that type of a quadrupole, you would just reverse them, all right? Okay, so this 4x4 matrix is representing the horizontally focusing, vertically defocusing quadrupole magnet, and you'd reverse these 4 elements to represent the vertically focusing and horizontally defocusing quadrupole. So that's what we have here. So now, here's the quadrupole. You have the matrix equation that starts out with the original x, x prime, y, and y prime of the proton, all right? Where it's at, horizontally displaced from the z-axis, how fast that position is changing with respect to its distance along the z-axis, its vertical displacement with respect to the trajectory, the z-axis, and how fast that's changing with respect to its distance along the trajectory, the z-axis. That's our original positions and how fast that position is changing for the proton. Now, it goes through the quadrupole. And when it comes out, here is its new position, x prime. It's new how fast it's changing with respect to that z trajectory